In this video, I want to walk us through how we can convert our high-level concepts of if statements that have else's, if statements with multiple conditions. How do we make those same control flow structures in assembly language, particularly the AT robots assembly language? So we're going to start with the most basic conditional statement, an if that doesn't have an else, just a true block. So in this code, there are two ways to think about it. Or two ways we have to think about it. First, say if dog is less than whatever value is in CX register. And I realize in high-level code like C we don't use registers. I'm just making that happen for the sake of these slides so that when we go to the assembly language, we'll have both variables and registers floating around in the code we see. I'll use immediate values later as well. Hopefully everybody's okay with that. So if dog is less than the value in CX, we're going to jump down here and increment dog. And when we're done with that, we move on past the if statement. In the false case, where this condition fails, if dog is greater than or equal to CX, then we're just going to skip on down here and pass the if and continue on with life. Now, both of those understandings are correct, but they require each other together to be wholly correct. And what beginning assembly programmers tend to get wrong is that they focus on the first one. So what we think, or what they tend to think, is that if dog is less than CX, then I'll write that conditional statement that says, well, let me do the comparison, and I'll jump on the less than condition down to some true code so we can increment dog. When we're done with that, we'll move on with life. And that seems quite natural. But it creates an error condition if this original if expression fails or has a false value. So think about it. If dog was greater than or equal to cat, but we only jumped past this code in the case that dog was less than CX, then the conditional jump would fail, but then we just run the next line of code, which increments dog. And that would be a mistake. So we're going to look at how to do this right on the code here to the right. So the first thing we do is compare dog to the CX register. And we're going to use inverted logic here. So we're going to jump on the opposite condition of what's over here. We're going to jump if the greater than or equal flag is set, meaning that dog is greater than or equal to CX. We're going to jump down to the label if end down here and move on with life. Otherwise, if dog happens to be less than CX, then this conditional jump, it will fail to take us anywhere. And so we just fall through to the next line of code. That's the true part of the code where we increment dog. And when we're done with that, we fall down past the end of the if statement and move on with life. So in order to do this right, we have to be thoughtful about the nature of this condition. Will it work for us in the true and the false conditions? And in the case of an if with no else, we have to use inverted logic. Now I want to take a quick moment to point out how I am formatting my code here. Not the business of laying it out into columns, but how I've actually used something like pseudo identifiers here. So down at the bottom is this label if end that we actually jump to from here conditionally. But then I have two other labels. One, or they look like labels, but they're comments. Here's one that says if, and here's one that says if true. What I'm doing here is using this comment to say, well, I'm starting an if statement of some kind. And here is the true block of it, and here's where it ends. Now, if I had more than one if statement in my program, which I am bound to, I would make this say something like if 1, if 2, if 3, for all the different ifs, and then I would use that as a prefix for the true blocks as well as the end label. That way, when I have nested ifs, ifs inside of ifs inside of ifs, I can tell what blocks belong to which if, like what the scope is at some higher level, even though all my code is in these two columns. And I think that's a coding standard everyone starting out in assembly language should adopt. All right, so let's look at an if statement that has an else, just a slightly more complicated statement. In this case, our code is checking to see if bx is not equal to 9. And if it isn't, then we're going to decrement the age variable. And when we're done with that, we need to just move on past all of the if code. On the other hand, if bx turns out to be equal to 9, then we want to jump down here and put into the variable cat whatever dog plus 5 is. Now, this line of code here I've done purposefully because it's a little tricky for beginning programmers. Because what we often tend to do is see this dog plus 5, and those beginners will say, well, add 5 to dog. And then they can move that new value of dog into the variable cat. But unlike this high-level code, what I just described actually modifies the variable dog because we add 5 to it. So we have to both get the control flow to work right for the true and false condition of this if. But we also have to make sure that in the false condition that we don't modify the variable dog, because the high-level code that we're working from doesn't modify the variable dog. So let's look at how we do that over here in this code. So at the top, we compare bx to 9. Notice this time that I'm not using inverted logic. I'm doing the same condition as what's over here. So I'm going to jump if bx does not equal 9 to the true part of my code. That's exactly what this says. Oops, let me go back. That's exactly what this says. So that means I'm going to go from here down here to the true portion of the code. And I'll decrement age. And then when I'm done with that, I'll end. Now, you may be wondering why I put the true code at the bottom. I'll get to that. Now let's look at the false condition. Let's compare bx to 9, and let's say they are equal to one another. Well, in that case, this conditional jump, the jump not equal, isn't going to take us anywhere. So we're going to fall through to the false code. And we're going to do cat equals dog plus 5. But I'm not going to add 5 to dog. Instead, I'm going to first copy dog into cat, its current value. We know we're going to clobber cat anyway, so this is okay. Then I can add 5 directly to cat, and now cat has the equivalent of dog plus 5 in it without modifying dog. Then I'm going to unconditionally jump past this true code, because I don't want to accidentally run the true code as well. I'm going to jump past it to the end of my if. So my control flow is logically correct. But there's still this mysterious bit where the C code has true and then false code. And what I've done is put the false code on top and the true on the bottom. And that definitely needs explanation. So when you've learned your high-level language and you started to learn about if statements that have else's, if you had a quality instructor or a quality textbook or both, hopefully, they probably told you a very simple idiom. Whatever of those two conditions is going to run most frequently, make that the true part of the code, meaning modify your condition so that the true portion of your if-else is the code that is going to run the most frequently. That's especially valuable in a high-level piece of code because what it does is it puts the condition, say here, and then the code that's going to run most of the time is right here, visually and contextually aligned. The else code, which runs more infrequently, is visually separated. It's disconnected. But that's okay. It'll be harder to understand the context of the else code because of that separation, but that's the code that doesn't run as frequently. So we need to make sure first that we have great comprehension on code that runs frequently. So we put the frequent code into the true. Now we're going to leverage that idiom in our assembly code here. So what I've done by putting the false code on the top and the true code on the bottom is I've actually made the true code execute faster. So let's take a peek at that. Right now we're going to forget about the meat, forget about decrementing age and setting cat equal to dog plus 5. Let's only focus on the code that actually controls the flow of the program. So in the beginning of this if statement, whether the condition will be true or false, we are definitely going to compare bx to 9, and we are definitely going to execute this instruction, jump not equal to if true. We just may not take the jump, but both of these lines will be executed. So we're going to execute 2 lines no matter what. If we go to the false code by falling through, then we skip past these 2 lines of code that are meat, and this last line, this unconditional jump, that's part of the control flow. Without it, we would fall into the true code and run it as well, which would be weird and incorrect logically, right? So that means to execute the false path for this sequence of code, I've got 2 instructions here and a third one here. For the true part of the code, I run the same first 2 instructions, but because the condition is true, I jump down to here, decrement age, and then the way I get out of the if is to do nothing but move on with life. So the true code has only 2 lines that have to be executed for control flow, whereas the false code has 3. And since the true code runs the most frequently, by giving it a 1-cycle advantage, I could drastically be improving the performance of this code with this model, considering that lots of code is just in big loops that are inside of other loops, inside of other loops. So that 1 cycle saved for the true is going to have a large benefit across the life of my program's runtime. All right, so let's look at a multi-condition if statement. In this case, I'm not going to include an else just because it'll make the code taller. I want to focus on the multiple condition. But here we have 2 conditions. We're looking to see if A is greater than B, or if B mod 2 equals 0, or if the remainder of B divided by 2 is 0. Another way to think of that still is B an even number or not? If the remainder when dividing by 2 is 0, that means B was an even number. Otherwise, it's odd. So when we have a piece of code like this at the high level, the one thing that we always try to recognize early is that the anchor to the multiple condition, the logical OR here, has a short circuit condition. Specifically, if A turns out to be greater than B, and that part of our multi-condition is true, then the whole thing is going to be true, because ORs only need one part to be true. So then it's a waste of time to bother looking at the second condition. So we need to make sure that that shortcut is in our assembly code. So let's look at that. We'll start the if out by comparing A to B, and notice that now, even though this is an if with no else, I'm using the same logic as the original C code. We always must think these things through to make sure it works correctly. So if A is in fact greater than B, I'm going to jump down to the true part of this code. And the reason I'm jumping down to the true is because I have to have code up here for the second condition. And if I'm going to do a shortcut for the OR, I'm basically skipping the second condition. That's why I have to make sure that this thing jumps past, not falls through. Okay, so jump greater than, just like this. And if that doesn't work out, then I'm going to fall through to the second half of the OR, the right-hand side of the OR condition, to check whether or not this is even. So in this case, much like the code where I put dog plus 5 into cat, what I don't want to do is divide B by 2 and store that result in B, because that's what the division or modulus instruction does. It takes its left argument and divides it by whatever the right argument is, and then it stores the result back into the left. So we don't want to change B. This is where we can get great use out of these registers. So I take a copy of that variable B and put it into the AX register, assuming that I'm not using the AX register for something else. Then I can do modulus by 2 directly on the value in the AX register, after which I'll compare to see if that remainder is 0 or not. And in this case, notice I'm going to jump on the not equal condition. So this is me saying jump down to the end of the loop, end of the if B mod 2 is not equal to 0. And that's because if the second condition fails, meaning the negative case, so negative logic, I need to skip past this code that puts 4 into X. So I have to skip past the true. So in this slick little piece of code, I'm using a positive condition, the same as the original C in one case, and a negative condition in the other. You just have to think it all through to make sure that it's going to work. So this way, if the first condition holds and the remainder is in fact 0, this jump won't take me where, because AX will equal 0, and I'll fall through to the true, just like we want, and move 4 into X. Otherwise, it skips down to the end, and everything's great. Now, you might wonder why I've highlighted these lines of code blue. It's not to separate the first condition from the second visually, although it does that. The reason I've highlighted these is because this one does some arithmetic. In particular, it's doing modulus division. And if you review the video on the AT robot instructions, you'll find that when we talk about division and multiplication and modulus, that each of those three instructions in the HE robots world take 10 cycles each. So they are expensive. At least they're more expensive than instructions that take only one cycle, like say addition or others. So what we're going to do now is improve the performance of this code. We're going to keep the control flow the same, but speed up the code. So the first way I'm going to do that doesn't change how many lines of code I have at all, but it dramatically reduces the number of clock cycles involved in running the code. So here what I do is I copy B into AX, just as we did before. But then I'm going to modify AX by doing a bitwise AND operation with the bit mask 1 hex. Now, traditionally, when I'm working in high-level code, I prefer to use compile time generated bit masks rather than hex strings for my bit masks, because you have to mentally decrypt what the hex means when you're going to interpret it. But AT-Robots assembly doesn't give me a way to do those assemble time dynamic bit masks. So instead, I'm just going to use a hex number here, and people who do a lot of assembly code will be used to seeing those things. Hopefully they always get written right and interpreted correctly. But in this case, what we're looking at is a bit string that's all zeros with a 1 in the least significant bit. And if you AND something with that, because of all the other zeros here for the high order bits, the result will have all the original high order bits zeroed out, and only bits where there was a 1 in the bit mask, in this case the lowest bit, the 0th bit, that one will pass through from its original value, which came from B. Now, if we were to do modulus division by 2, and this was an even number originally, B was an even number, that low order bit would be a 0, because otherwise it would have had 1 added to it and it would have been an odd number. If it was an odd number, there would have been a 1 in that bottom bit. So by masking away all bits but the bottom, I get whether or not it was even in the case that it was a 0, or odd in the case that it wasn't. So this code does exactly the same thing as the previous code we saw, but instead of this one instruction in the middle that costs 10, making this 3-step sequence worth 12 cycles, I introduce an AND operation which only costs a single cycle. So I went from 12 cycles to 3 cycles, which is a great improvement. Now I want to look at one last slide where I improve this one more time and make it extra nice. So in this case, what I've done is dropped the length of the code down from 3 statements to a single statement by leveraging that test instruction that we talked about in a previous video. So here I don't have to back up B into AX, because I'm not going to manipulate and store the results of any operation. Testing is doing the same thing as a bitwise AND, remember that, but it doesn't store the result. It only affects the flag register. So now I can use the same bit mask and it against the original variable B using the test instruction, get my flag set, and I don't even have to do the comparison because this sets the flag. Whereas in the previous version, I had to use a comparison to set the flag. And so then I can just do my conditional jump immediately after. So I get down to a single line of code instead of 3, which makes the program shorter. And if you're doing, say, a lightweight tournament where you're restricted to the number of lines of code that you can have, this is important. And it also drops me down to a total of 2 cycles. Now, why 2 cycles for one instruction? Well, if you go back to the instruction video, you'll see that the test instruction takes 2 cycles instead of 1. All right, so then we've done all the major conditional statements we can. There are plenty more you could construct, of course. You could do else ifs, but I want you to think about that, because if you do, you'll quickly realize that an else if statement is really just an if else where that next if is just embedded inside the scope of the else. And so very simply, with comparison statements, or like in this code here, a test statement, we're able to get our flag set and use conditional jumps to move us forward in the code. We just have to make sure we use the right logic when we do. So always double check whether you needed the positive or the inverted logic. Just think it through on both the true and false conditions, and everything's going to work out great.